Hi everyone, this is Mrs. J, and today we are going to be talking about solving systems of linear equations. I have a quick warm-up for you guys, so please pause the video and give it a try. All right, go ahead and check your work here. So for part A, I used that point slope form, and then I just rewrote it in standard form. So remember, A must be positive, and A, B, and C must all be integers. So we can't leave this C value as 5/2. And then for part B, we'll start by finding the slope. You'll notice that these have the same y value, so the slope is actually 0. So you can just go straight to y equals 2 because you can recognize this is just a horizontal line that goes through the value y equals 2, or you could use the point slope form and you'll get that same answer. All right, so today instead of just solving a single equation with one variable, we're going to be solving what's called a system of equations, which is a set of two or more equations that have the same variables. So today we're going to be working with systems of two variables, which means we're going to be solving for both x and y. So essentially when we're solving a system, what we're looking for is where those two linear equations cross. We're looking for that point of intersection. So if you're working with two linear equations, there's three things that could happen. It's very possible for them just to cross one time. So you would have one solution. And what this means is that your equations have different slopes. So if you have two linear equations that have different slopes, they are going to cross somewhere. So you can always find that solution. So in terms of classifications, here's just a little bit of terminology. For a system like this with that one solution, we would call this consistent. Consistent just means that a solution exists, and then we would also classify this as an independent system, meaning that there is only one, there's exactly one solution. Now, it is also very possible when you have two linear equations that they never cross. So if the two equations never cross, then you have zero solutions or no solutions. And this is really only going to happen when you have the same slope with different y-intercepts. But essentially, if you have the same slope with different y-intercepts, they're traveling at the same speed. The rise over run is the same, so they will never cross. And that means that this system is inconsistent. That's how we would classify it, because there are no solutions. Now, this one, it's hard to see. I know this looks like one line, but this is actually a system where it is essentially two equations that make the same line. So when you have this scenario, they're literally on top of each other, which means that you actually have an infinite number of solutions, because there's an infinite number of times that they are intersecting because they're literally on top of each other. When you have something like this, this will occur when you have the same slope and the same y-intercept. And for one like this, we would call it consistent because there's at least one solution, but we would call it, rather than independent, we call it dependent, because there are infinitely many solutions. So you are either going to have one solution, exactly one, or exactly zero, or infinite. Those are the three options when you're working with a system of two linear equations. So one way you can solve a system of linear equations is by graphing and actually looking at your graph for that point of intersection. So let's give this one a try. I'm going to rewrite each of these in slope-intercept form just to make it a little bit easier to graph. So for this first one, we'd have y equals 5x minus 3. And for this second one here, we would have y equals x plus 5. So we graph those two equations, do it on this axis below. So for the first one, my y-intercept is -3 and my slope is 5. Then for my second equation, my y-intercept is 5 and my slope is 1. So really you just need to continue that on far enough for the two lines to intersect. And then again, our solution is that point of intersection right here. So we're actually going to write our solution as a coordinate, and that coordinate is 2, 7. So again, we're always going to write our solution as an ordered pair because we are looking for a point of intersection. All right, let's try another one together. So again, I'm going to rewrite in slope-intercept form so it's easier to graph for this first one. So 2y equals negative 7x plus 16. And for our second one, we'll have negative 6y equals 21x plus 24. So we have y equals negative 7 over 2x minus 4. So right off the bat, you might notice that we have that scenario where we have the same slope with different y-intercepts. So at this point, if you notice that, you could say no solution. But just to show you graphically how that will look, you will see that your lines literally will not cross. So here's our first line. It looks something like this. And our second line, here's our y-intercept. And that also has a slope of 7 over 2. So it looks like this. So you can see that these are parallel lines. And parallel lines will always occur when you have that same slope. And so they will never cross. So again, we have no solution. Let's try one more together. So again, I'm going to rewrite both of these in slope-intercept form. So for this first one, we get 8y equals 2x minus 14. So y equals 1/4 x minus 7/4. For the second one here, we would get 4y equals x minus 7. So y equals 1/4 x minus 7/4. So just by rewriting it in that slope-intercept form, we see that we literally have the same equation. So I mean, you could graph it, but you're literally graphing the same thing on top of each other. So here you would just kind of have to estimate where negative 7/4 is. So about here. Then to follow that slope, you're just going to need to kind of estimate, but just do your best there. And again, you don't really even need to graph this because we know it's just going to be the same line on top of each other, and they are intersecting at every single x value. So here we have, again, infinite solutions. So there we've kind of gone through the three cases that you'll see with these types of systems when we solve by graphing. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So I rewrote both equations in slope-intercept form and graphed, and I found that they intersected at the coordinate negative 1, 4. I do want to point out two things. One, you could always check your solutions by plugging in your x and y values into each equation and make sure that they maintain a true statement. So that could be something to do if you have extra time on a test or quiz. You can see if your answer is correct by substituting the x and y values. Second thing I want to point out is that solving by graphing really only works if your lines intersect at a nice coordinate, meaning a coordinate that you can see the exact value. However, it's very possible for our lines to intersect, somewhere in between. So if that were the case, we would not want to use graphing to solve. We don't want to guess where that point of intersection is. So this really only works if you have a really nice solution, which is why we need to know other ways to solve. So we're going to move on to solving algebraically next. So there's two main ways we can solve a system algebraically. The first is using what's called substitution. So for substitution, we try to isolate one variable in either equation and then we substitute it into the other equation. So for this, you're going to want to kind of pinpoint which variable seems easiest to isolate. So maybe I'm going to work with the second equation here, and I'm going to try to isolate x. I'm going to move everything else to the other side. So I see x equals negative 2y minus 12. And now I know a way to define x in terms of y. I'm going to take that and I'm going to substitute it into the x for the x value in my other equation. So we have 8 times negative 2y minus 12 minus 3y equals negative 1. So you can see when I make that substitution here, now my equation only has a single variable. It's all in terms of y, which means that I can solve. So now we just go through and distribute and solve. So here we're able to solve and we get y equals 5. Then once I know one of my solutions, I can take it and I can substitute back into my other solution. I can use that original form or I can use this form right here. It's already isolated for x, so maybe this is the easiest route to go. So we have negative 5 minus 12, so x equals 10 minus 12, which is negative 2. So we'll want to write our final answer as an ordered pair. And again, we could easily check our solution by substituting for x and y in both equations. Let's try another one together here. Here you can see that this one actually has already isolated one of our variables, so for y. So I think the easiest thing to do would just be substitute it into that top equation. So we have negative 10x plus 5 times 2x minus 11 equals negative 30. So again, that substitution step makes it so we have a single variable, which means we can solve. So here you'll see something kind of interesting happening. Here actually our other variable disappears and we're left with the statement negative 55 equals negative 30. So whenever your variable disappears altogether, it's going to be one of two things. It's either going to be no solution or infinite solution. And the way you know is you have to look at what's left over. If the leftover statement, negative 55 equals negative 30, is not true, like it is in this case, negative 55 is not equal to negative 30, that's when you know that you have no solution. Now, if you're left with a true statement, like 0 equals 0, then that's a case where you would actually have infinite solutions. But here, again, if your variable disappears altogether and you're left with a false statement, we know that this is going to be no solution. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So I use this first equation to solve for y, which I substituted here into the second equation, got x equals 0, plugged it back in and got y equals negative 3. So just remember 0 is just like any other number. It's completely fine for one of your variables to equal 0. All right, so sometimes the substitution method isn't the most efficient method to use. So another really common method is called the elimination method, or sometimes called the addition method. So our goal is to add our equations vertically with the aim of eliminating one of our variables. And we can eliminate if the coefficients are opposites. So you have to look at your system and decide which variable you want to eliminate. So we could eliminate the x's. We would need to turn this negative 2 into a positive 4. So I can multiply our top equation by negative 2. Or if you notice, these two equations are already both negative 9. So if I simply multiply one of the equations by negative 1, it turns them into opposites. And then you'll see what happens. So I'm going to multiply our top equation by negative 1. And then I'm just going to rewrite our bottom equation here. And then you can see if I add vertically, we get negative 2x, and then the y's eliminate, they disappear. And then we have equals 2, and that allows me to finish solving for my other variable. So x equals negative 1. And then just like with the substitution method, once you have one variable, you can go back and substitute it into either equation to find the other. So I'll just substitute into that top equation. So negative 2 times negative 1 minus 9y equals negative 25. So negative 9y equals negative 27, which means that y equals positive 3. So again, we didn't have to eliminate the y's. It just seemed like for this particular problem, it was the easiest way to go. All right, let's try one more problem together. So for this one, if we want to eliminate our x's, we would multiply by negative 3 to our bottom equation. It would actually be the same for the y's, so this is kind of an interesting problem. So regardless, to make opposite coefficients, we're going to multiply both sides by negative 3, and you'll see what happens for this one. So I'm going to rewrite both equations just to make it easy for me to keep my work organized. So here you can see that both x and y eliminate. So on the left side of our equation, we just have 0. But then on the right side of the equation, we have 8. And this is like case like we talked about before. If your variables disappear, but you're left with a statement that is not true, this is when you would have no solution. But if you're left with a statement that is true, sometimes both variables will eliminate, but you'll get 0 equals 0. That's a case when you would have infinite solutions. Okay, so I have one last problem for you to try on your own, so please pause the video and hit play when you're ready to check. All right, go ahead and check here. So this is a case where you would have to actually multiply both equations by something to create those opposite coefficients. So I chose to eliminate my x's. You could have also eliminated your y's by multiplying the top equation by 4 and the bottom equation by 5. Either way is fine. It's whatever looks easiest to you. You should get the solution negative 2, 1. And again, you can always check your solution by substituting x and y into both equations. All right, that is all for today's video. Thank you so much for watching.